Imagine materials born from a clever partnership. They are not just one substance but many, intricately combined. Each component brings its unique strengths to the union. Together they forge something entirely new, something often far superior to the individual parts. These are composite materials. They are engineered marvels, meticulously designed at a microscopic level. We are witnessing their influence expand dramatically every single day. It is a quiet yet profound revolution reshaping the world around us. This revolution is happening in the objects we use daily, and the vast structures that underpin our modern civilization. Why is there such a growing excitement surrounding these composite materials? Think about the fundamental properties engineers crave: strength and lightness. Composites frequently deliver both in abundance. For centuries, traditional materials often forced a difficult compromise. You could have immense strength, but it usually came with significant weight, or you could opt for lightness, but then you might sacrifice robustness. Composites elegantly sidestep these age-old constraints. They are the featherweights of the material world that can possess the resilience of heavyweights. This remarkable combination unlocks a universe of incredible possibilities for innovation and design across countless fields. The demand for these advanced materials is experiencing an explosive surge. Consider the aerospace industry, constantly seeking ways to reduce weight and improve fuel efficiency. Look at the automotive sector, striving for lighter vehicles that are both safer and more environmentally friendly. Even the construction industry, which builds the very fabric of our cities, is turning to composites. And let's not forget the world of sports, where equipment made from composites helps athletes shatter records. All these diverse sectors are enthusiastically embracing composites. They clearly recognize the transformative potential. They understand the distinct advantages these materials offer over conventional options. This is far more than just a fleeting trend. It signifies a fundamental, perhaps even epochal shift in material science. We are transitioning from an age dominated by simple metals, wood, and basic plastics into a new, more sophisticated era. We might call it the composite age. These materials are not merely straightforward replacements for older substances. They are powerful enablers, paving the way for entirely new designs and previously unattainable capabilities. They consistently push the established boundaries of what we believed to be possible. They challenge our brightest engineers and visionary designers to dream on grander scales than ever before. As we observe from our vantage point in mid-2025, the pace of innovation is truly breathtaking, hinting at a future built on ingenuity. The aerospace industry was one of the earliest adopters of composite materials, and for very good reasons. When you're trying to send humans and machines into the sky or even beyond, every single gram matters. Carbon fiber composites, for instance, are a cornerstone of modern aircraft construction. Think of industry giants like the Boeing 787 Dreamliner or the Airbus A350. Significant portions of their airframes are made from these advanced materials. This makes them lighter, stronger, and critically more fuel efficient. Less weight means less fuel burned, which is good for the airline's budgets and even better for our planet's delicate atmosphere. These materials are silent heroes of the skies. Innovative manufacturing processes are also key to unlocking the full potential of aerospace composites. Take, for example, resin film infusion, often abbreviated as RFI. Companies like GKN Aerospace have pioneered this technique. It was notably used for molding parts for the fixed trailing edge of the massive Airbus A380's wings. Such processes allow for the creation of large, complex, and highly integrated structures with exceptional precision and strength. These advancements in manufacturing are just as crucial as the materials themselves. They ensure that the theoretical benefits of composites can be realized in practical, reliable, and increasingly cost-effective ways, pushing aerospace engineering to new heights of performance and efficiency. Our exploration of the cosmos also benefits immensely from composite technology. Just last year, in 2024, NASA's Advanced Composite Solar Sail System, or ACS-3, successfully deployed its innovative composite boom and sail system. This mission tested novel composite boom technology. These booms are stiffer, significantly lighter, and more thermally stable than previous designs. Imagine a spacecraft pushed by sunlight itself using vast, ultra-light sails. That's the promise ACS-3 is helping to realize. The success of such missions could inform future large-scale space endeavors, enabling us to venture further and learn more about the universe we inhabit. It's a testament to how these materials are literally helping us reach for the stars. And the journey doesn't stop there. Consider NASA's Europa Clipper spacecraft, which embarked on its long voyage to Jupiter's intriguing moon Europa in October 2024. This is NASA's largest spacecraft ever designed for a planetary mission. Its main spacecraft body involved careful composite design considerations to ensure it could withstand the harsh conditions of deep space while carrying its precious scientific instruments. The continuous adoption and refinement of composites in aerospace underscore their indispensable role. They are not just building aircraft, they are building the very vessels of discovery that expand our understanding of the universe, enabling us to explore new frontiers and seek answers to some of humanity's oldest questions. The automotive world is undergoing a profound transformation, and composite materials are right in the driver's seat of this revolution. For decades, steel was king, but the times are changing rapidly. Car makers are relentlessly pursuing ways to make vehicles lighter. Lighter cars mean better fuel economy for traditional engines. For electric vehicles, or EVs, lighter weight translates directly into longer range on a single charge. This is a critical factor for consumer adoption. Natural fiber-reinforced polymer composites, often called NFRPCs, are becoming increasingly popular. These materials combine plant-based fibers with polymers, offering a sustainable and cost-effective route to shedding kilograms from vehicle components. This shift towards lighter materials is not just about performance. It's also deeply connected to environmental responsibility. Reducing vehicle weight helps automakers meet increasingly stringent emissions regulations around the globe. Every gram saved can contribute to a smaller carbon footprint over the vehicle's lifetime. Think about the energy saved, not just in driving, but also in the manufacturing process of these lighter components. Moreover, the automotive industry is exploring composites for a wide array of parts, from body panels and chassis components to interior elements and even sophisticated braking systems. For example, BASF launched a new line of advanced thermoplastic composites, specifically for automotive applications, in September of last year, 2024, signaling strong industry commitment. Automation is playing a crucial role in making composite manufacturing viable for the high-volume demands of the automotive sector. Techniques like automated fiber placement and the use of sophisticated robotic manufacturing cells are enhancing production speed, consistency, and cost-effectiveness. These automated systems can lay down composite fibers with incredible precision, creating complex shapes that might be difficult or impossible to achieve with traditional metal stamping. This level of automation is essential to bring the benefits of composites from niche, high-performance supercars to the everyday vehicles that millions of people rely on. It is a marriage of material science and advanced robotics, working in perfect harmony. The future of automotive composites looks incredibly bright and diverse. We're seeing ongoing research into new types of natural fibers, improved resin systems, and faster curing processes. The goal is to make composites even more sustainable, more recyclable, and more affordable. Imagine car parts that are not only strong and light but also derived from renewable resources, contributing to a circular economy. This isn't science fiction, it's the direction the industry is actively heading. As we move further into 2025, the integration of these advanced materials will continue to accelerate, leading to cars that are safer, more efficient, and kinder to our planet. It's an evolution on wheels. The construction industry, often perceived as traditional, is increasingly embracing the innovative potential of composite materials. For builders and architects, composites offer a compelling suite of advantages. One of the most significant is their exceptional resistance to corrosion. Unlike steel, which can rust, or wood, which can rot, many composites are impervious to environmental degradation. This means longer lifespans for structures and significantly reduced maintenance costs over time. Think of bridges in harsh coastal environments or buildings in humid climates. Composites can stand strong against the elements year after year, decade after decade, requiring far less upkeep and repair. Design flexibility is another major draw for the construction sector. Composites can be molded into complex shapes and forms that would be challenging or prohibitively expensive to achieve with conventional materials like concrete or steel. This freedom allows architects to create more innovative and aesthetically daring structures. Imagine sweeping curves, intricate facades, and lightweight yet robust load-bearing elements. Furthermore, the inherent lightness of many composite components can simplify transportation and on-site assembly, potentially speeding up construction timelines and reducing the need for heavy lifting equipment. This can lead to safer construction sites and more efficient building processes overall, transforming how we envision and erect our built environment. A particularly exciting development is the rise of green composites in construction. As the world focuses more intensely on sustainability, the building industry is seeking materials with lower environmental footprints. Green composites often incorporate natural polymers and biomass-derived products. They might use reinforcements made from renewable resources like flax, hemp, or kenaf fibers instead of traditional glass or carbon fibers. This shift towards bio-based materials aligns perfectly with the principles of sustainable development and the circular economy. It's about building structures that are not only durable and efficient, but also more harmonious with the natural world, minimizing waste and reliance on finite resources. The applications for composites in construction and infrastructure are diverse and expanding. We see them used in pedestrian bridges, cladding for buildings, strengthening and retrofitting existing concrete structures, and even in innovative approaches like 3D concrete printing where composite fibers can be integrated for enhanced strength. Organizations like the National Composites Network play a vital role by providing expert support to companies looking to adopt these advanced materials within the construction sector. As we continue through 2025, the integration of composites promises to make our buildings and infrastructure more resilient, more sustainable, and more inspiring for generations to come. It is truly building the future, one composite component at a time. Section 5. Guardians of Strength, Composites in Defense and Sporting Arenas. In the demanding world of national defense, materials are often pushed to their absolute limits. Here, high-performance composites have become indispensable. Their superior strength-to-weight ratios are a game-changer. Imagine armor systems that offer better protection for soldiers and vehicles, yet are significantly lighter than traditional steel armor. This lightness improves mobility, reduces fuel consumption for vehicles, and lessens the burden on personnel. Durability is another critical factor. Defense equipment must withstand extreme conditions, from harsh climates to the stresses of combat. Composites can be engineered to offer exceptional resilience and longevity, ensuring reliability when it matters most. The applications in defense are varied and vital. We see composites used in advanced composite armor systems, providing enhanced ballistic protection against a range of threats. They are integral to the construction of modern military aircraft, naval vessels, and ground vehicles, contributing to their speed, maneuverability, and survivability. Components like missile casings, radomes which protect radar equipment, and unmanned aerial vehicle structures all benefit from the unique properties of composites. Furthermore, materials like aluminum metal matrix composites are finding specialized roles, offering a unique blend of lightness, strength, and thermal properties suitable for demanding defense and aerospace applications. These materials are silent guardians, enhancing safety and effectiveness. Now let's shift our gaze from the battlefield to the sporting arena. Here too, composites are enabling athletes to achieve new heights of performance. The quest for lighter, stronger, and more responsive equipment is relentless. Think about a Tour de France cyclist. Their bicycle frame, likely made from carbon fiber composites, is incredibly light yet stiff, translating every ounce of the rider's effort into forward motion. Consider a tennis player's racket, engineered with layers of composite materials to provide power, control, and vibration damping. Or the sleek, hydrodynamic hull of a racing yacht, cutting through the water with minimal resistance thanks to advanced composite construction. The sports industry is also increasingly mindful of its environmental impact. This has led to a growing interest in biocomposites. For example, researchers and manufacturers are exploring the use of materials like banana fiber reinforced hybrids. These innovative composites aim to reduce the reliance on petroleum-based materials and lower manufacturing costs, all without compromising the performance characteristics that athletes depend on. This pursuit of sustainability, coupled with the drive for peak performance, is leading to exciting new material developments. From golf clubs to hockey sticks, from skis to surfboards, composites are helping to redefine the boundaries of human athletic achievement, making sports faster, more exciting, and increasingly eco-conscious. Section 6. The Next Frontier: Smart Materials and High-Entropy Innovations. The world of composite materials is not standing still. Far from it. Scientists and engineers are constantly pushing the boundaries, exploring truly cutting-edge concepts. One of the most exciting emerging trends is the development of high-entropy composites, sometimes referred to as HX. Traditional composites usually involve a primary matrix material and one or two types of reinforcement. High-entropy materials, however, take a different path. They are complex systems, often involving multiple principal elements in near equal proportions. This can lead to unique microstructures and consequently extraordinary combinations of properties, think exceptional strength, remarkable fracture toughness, and stability at extreme temperatures. This is a new frontier in material design. Another fascinating area is the development of multifunctional materials. Imagine a composite component that doesn't just provide structural support. What if it could also store energy, sense damage, or even communicate? Researchers are working on embedding electronics directly within composite structures. Future composites are expected to integrate sophisticated electronic and optoelectronic functionalities. This could lead to aircraft wings that monitor their own structural health in real time, or car bodies that act as giant batteries. The possibilities are truly mind-boggling, blurring the lines between material and device. We are talking about materials that are active, responsive, and intelligent in ways we are only beginning to comprehend. This brings us to the realm of smart composites. These are materials designed with self-sensing and even self-healing capabilities. Imagine a tiny crack forming in a composite structure. A smart composite could detect this damage instantly, perhaps through a network of embedded fiber optic sensors. It could then alert operators or even initiate a self-repair process. Self-healing mechanisms might involve microcapsules filled with a repairing agent, which rupture when a crack appears, releasing their contents to fill and bond the damaged area. This technology could dramatically improve safety and reduce maintenance costs for everything from bridges to spacecraft, extending their operational lifespans considerably. Furthermore, the integration of nanomaterials like graphene and carbon nanotubes is opening up yet another avenue for enhancing composite performance. These incredibly small yet exceptionally strong materials can impart remarkable improvements in mechanical strength, electrical conductivity, and thermal properties even when added in tiny quantities. Advanced additive manufacturing, commonly known as three-dimensional printing, is also revolutionizing how we create complex composite geometries, allowing for optimized designs and rapid prototyping. As we look forward from 2025, these emerging trends promise to elevate composite technology to unprecedented levels of sophistication and utility, making our world smarter, stronger, and more resilient. Section 7. The Green Imperative: Sustainability and Recycling in the Composite Lifecycle. As composite materials become more widespread, the focus on their environmental impact intensifies. It's a critical consideration for a sustainable future. The green imperative in the composites industry involves a multifaceted approach. It starts with the development of more sustainable composite materials themselves. This includes using bio-derived resins and natural fibers, as we've seen in automotive and construction. The goal is to reduce reliance on fossil fuels and create materials that are biodegradable or have a lower carbon footprint from cradle to grave. This means thinking about the entire life cycle, from raw material extraction to end-of-life disposal or ideally reuse. Improving recycling techniques for existing and future composites is a major area of research and development. Composites, particularly thermoset composites, which are common in aerospace and automotive, have traditionally been challenging to recycle. However, significant progress is being made. Chemical recycling methods aim to break down the composite matrix, allowing for the recovery of valuable fibers and chemicals. Mechanical recycling involves grinding down composite parts to be used as fillers or reinforcements in new products. Both approaches are crucial for minimizing landfill waste and conserving resources. The aim is to create a more circular economy for these advanced materials. Recent research highlights this concerted effort. For instance, a review published in 2024 by Piraye and Sarvia detailed advances in polymer composites, their manufacturing processes, and importantly, their recycling methods and overall sustainable practices. Looking ahead, further research anticipated in 2025, such as the work by Kumar and colleagues, will continue to explore recent developments in the mechanical properties and, crucially, the recycling of fiber-reinforced polymer composites. These academic and industrial efforts are vital. They provide the scientific foundation for developing scalable and economically viable recycling solutions that can handle the increasing volume of composite waste as these materials proliferate. The ultimate goal is to minimize the environmental impact of composites throughout their entire existence. This involves not only developing greener materials and effective recycling methods, but also conducting comprehensive life cycle assessments. These assessments help us understand the full environmental cost, from raw material extraction and manufacturing energy to in-use performance benefits like fuel savings and end-of-life options. By taking this holistic view, the industry can identify areas for improvement and ensure that the remarkable benefits of composite materials do not come at an unacceptable cost to our planet. As of 2025, this sustainable mindset is increasingly embedded in the DNA of composite innovation. Section 8. Navigating the hurdles challenges in the composite landscape. Despite the remarkable advancements and growing adoption of composite materials, there are still significant hurdles to overcome. One of the primary challenges is often the high initial production cost associated with some advanced composites, particularly carbon fiber-based systems. The raw materials themselves can be expensive, and the manufacturing processes are often more complex and energy-intensive than those for traditional materials like steel or aluminum. While costs are gradually decreasing with economies of scale and technological improvements, making composites more broadly affordable, especially for mass-market applications, remains an ongoing endeavor for researchers and industry players alike. This economic factor is a key consideration for wider adoption. Another significant challenge lies in the specialized manufacturing processes required for many composite materials. Techniques like automated fiber placement, resin transfer molding, and autoclave curing require sophisticated equipment and skilled personnel. Developing faster, more efficient, and less capital-intensive manufacturing methods is crucial. Furthermore, ensuring consistent quality and minimizing defects in composite parts, especially those with complex geometries, demands rigorous process control and non-destructive testing methods. Scaling up production to meet the burgeoning demand from sectors like automotive and wind energy, while maintaining high-quality standards, presents a continuous engineering and logistical challenge that the industry is actively addressing. Material standardization is also a key area that needs continuous attention. Unlike traditional metals, which often have well-established international standards for their properties and performance, the world of composites is incredibly diverse. There are countless combinations of fibers, resins, and manufacturing techniques, each resulting in materials with unique characteristics. While this offers incredible design flexibility, it can also make it more difficult for engineers to select materials and predict their long-term behavior with absolute certainty. Developing more comprehensive databases, standardized testing protocols, and robust predictive models is essential for building greater confidence and streamlining the adoption of composites across various industries. Finally, as we discussed earlier, recyclability and end-of-life management remain a prominent concern. While progress is being made, developing cost-effective and environmentally sound recycling solutions for all types of composites is a complex problem. Conducting comprehensive lifecycle assessments for composite products is also vital, but can be intricate due to the many variables involved. These assessments are necessary to truly understand the overall environmental footprint and to guide the development of more sustainable solutions. Overcoming these challenges, cost, manufacturing complexity, standardization, and end-of-life management, is paramount for unlocking the full, world-changing potential of composite technologies in the years to come. Section 9. Synergy and Progress. The Power of Collaboration and a Look Ahead. No single company or research institution can unlock the full potential of composite materials alone. The path to innovation and widespread adoption is paved with collaboration. Cross-sector partnerships are absolutely vital. When experts from aerospace, automotive, construction, and other industries come together, they can share knowledge, identify common challenges, and develop synergistic solutions. For instance, a breakthrough in low-cost carbon fiber manufacturing for the automotive sector could also benefit aerospace or sports equipment. This cross-pollination of ideas accelerates progress for everyone involved, creating a virtuous cycle of innovation and application across disparate fields. Innovation ecosystems and dedicated research centers play a pivotal role in fostering this collaborative spirit. Organizations like the Composites Innovation Center and the National Composites Network provide crucial platforms for industry, academia, and government to connect, share resources, and spearhead joint research projects. They help bridge the gap between fundamental research and industrial application. We see tangible results from such efforts, like the National Composites Network providing expert support specifically to companies in the construction sector, helping them navigate the complexities of adopting new composite technologies. Recent partnerships such as Hexcel Corporation teaming up with the University of Bristol in July 2024 to advance carbon fiber applications further underscore this collaborative trend. Looking at the global landscape, the advanced composites market is truly dynamic. North America currently dominates with a significant market share, largely driven by its robust automotive and aerospace sectors. However, Europe is expected to see substantial growth, particularly fueled by its ambitious wind energy targets and strong aerospace demand. Key companies from around the world, including names like Hexcel, Toray, Solvay, and Teijin, are constantly innovating and investing heavily in research and development. This global competition, coupled with collaborative efforts, ensures a rapid pace of advancement in composite material science and engineering, pushing the boundaries of what these remarkable materials can achieve. As we stand on the cusp of further breakthroughs in 2025, the future of composite materials looks exceptionally bright and transformative. From the deep sea, where corrosion-resistant composites are used for pipelines, to the vastness of space, where lightweight structures enable ambitious missions, their impact is pervasive. Emerging trends like smart materials, high-entropy alloys, and sustainable biocomposites promise to further revolutionize how we design and build everything around us. The journey of composite technology is a testament to human ingenuity. It is a continuous quest for materials that are lighter, stronger, smarter, and more sustainable, shaping a future that is both technologically advanced and more in harmony with our planet. The composite age is well and truly upon us.